Okay, now let's get to Simpson's rule in general, where we're integrating a function from some number a to some number b, and it doesn't necessarily have to be evenly spaced around or symmetric about x equals 0. First, a couple of points. Simpson's rule is greater than trapezoidal rule. As I mentioned earlier, we can throw the trapezoidal rule away now. Even though it's a good method, Simpson's rule is superior to it. You actually, you don't need a smaller h. I think I kind of can use. How about don't need as small of an h value. Don't need a small h compared to the trapezoidal rule. It does require that you use evenly spaced points. Well, it's not an absolute requirement, but it just makes it much easier. Yeah, it'll get more complicated if you don't. We have 3 points per interval. So 3 consecutive points like xi plus 1, xi plus 2, 3 points in a row will make an interval. Requires an even number of intervals. Just as an example, here's an even number, and notice that this will work. Simpson's rule is going to use this one computation for these 3 points, and then shift over to here, one computation with these 3 points. So this number needs to be even, which means you'll have, this is the number of intervals, 1, 2, 3, 4. So just make sure that you have an even number of intervals. H, if it is too small, could cause you problems in the computer with this algorithm. Remember what happens when you subtract small numbers that are very, very close together. That can cause problems with the computer, and you may not even know. It may just give you erroneous results. So that's something to be aware of. Okay, let's adapt Simpson's rule to just a generic interval from A to B. These are the grid points. A is always the left endpoint. B is always what we call the right endpoint, but we can refer to them as x0 and xn. So x0 up to xn, where n has to be an even number. Well, let's take a look at what the integral is. We want to go from A to B, or x0 to xn of f of x dx. The approximation is going to look like this. Well, this is an equal sign. You need to get used to this indexing. We're only going up to n over 2 because remember, we are only using n over 2 Simpson's rule intervals. If n was 4, we only had 2 intervals. Remember the 0, 1, 2 and the 2, 3, 4. So k is going from 1 to half of the number of intervals. And we're taking, in each case, the integral from this to this. And let's just loop through that and make sure it works correctly. K starts at 1. So what is this integral going to go from? The bottom limit to the top limit. If k is a 1, we're starting at, well, 1 minus 1 is 0, x0, and the top better be x2. If k is a 1, it is exactly right. So we're going from x0 to x2, and then, shouldn't have erased that before, that's the first interval, and then k bumps up to a 2. Well, 2 times 2 minus 1, that's 2. 2 times 2 is 4, so that takes us to here. And if n were bigger than that, then we'd go from x4 to x6, x6 to x8, and so on. Okay, so here's where we're getting to the approximation of Simpson's rule. I'm going to go ahead and keep the summation, k going 1 to n over 2. And now we're going to do the Simpson's rule approximation for this. So the way I'm going to write it is h over 3, because remember those, the three numbers were 1/3, 4/3, 1/3. I'm factoring out the 1/3. And then we were going to get this times f sub x 2k, 2 times k minus 1, this guy right here. And then all of that, let me see, let me put a, yeah, I don't need a square bracket, that's good. So that's like a 1/3. This is going to be a 4 because it's like 4/3. And all we're going to do is take one more than this in the index. And I could have simplified that index, but I just want to make it obvious. We're starting at this number, 2 times k minus 1. The next one is going to be that plus 1, and then the next one is going to be plus 2. Okay, that's the formula, but that is even inefficient. Because remember, I should just leave this up here, x0, let's say that's x4, x1, x2, x3. The first summation, when k is 1, it's looking at f of this, and f of this. Right here, f of x0, f of x1, f of x2, and multiplying them by, well, some of them by a number. But the next time, k becomes a 2. This is going to go from f of x2, f of x3, f of x4. F of x2 was already computed in the previous iteration. So we shouldn't have to plug x2 into the function again. Over time, that's going to be very expensive, especially when this is a wide interval. You're getting lots of redundancy. When there's more than x0 to x4, x0 to x400, there'd be a lot of redundancy in that. Okay, so I'll just make a note that this is redundant in the processing, that endpoint is. Because I've got a fairly long line that I want to write, I'm going to bring this down and put an equals right here. So this thing right here is equal to, let's see, if I want to get rid of this summation, it's going to be an h over 3. And then remember, when k is a 1, this is x sub 0, x sub 1, x sub 2. So I'm going to get f of x0 plus 4 f of x1 plus f of x2. These three terms are just when k is equal to 1. Now let's do the second case. When k is equal to 2, it's going to go 2, x sub 2, x sub 3, x sub 4. So I'm going to get f of x2 plus 4 f of x3 plus f of x4. This is from the k equal 1. This is from the k equal 2. And so on. Maybe I'll go all the way to the last one. Plus dot, 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 plus f of x in minus 2 plus 4 f of x in minus 1 plus the last one, f of x in. And this would be the case where k is n over 2. Remember, n is an even number, so that's definitely an integer. So the final line, h over 3. Let's just combine everything that we can. Notice that this is going to show up twice. So x2 is, f of x2 is going to be 2f of x2. Well, notice that the same thing is going to happen for 4. F of x4 is going to show up twice. And so on. And this one is going to show up twice. So let's see what the coefficients are going to be. F of x0 just shows up one time. 4f of x1 and then 2f of x2s, plus 4f of x3s. But f of x4 shows up twice. One of them's in this dot, dot, dot. So plus 2f of x4. And it's going to repeat coefficients 1, 4, 2, 4, 2, 4, 2, 4, and then it's going to end up with just a 1. So I'm going to put plus dot, 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 plus, this one's going to show up twice, 2f of x n minus 2 plus 4f of x n minus 1 plus f of x n. This is Simpson's rule for the approximation of the integral from x0 to xn. Very simple to compute and quite accurate even when h isn't extremely small. So very, very powerful tool.